Today in 8.2 we're going to work on solving exponential equations, writing exponential functions, and working on compound interest. First of all, I've got sort of this base number table, and you've seen these before. These are some of the most common powers that hopefully you're starting to become familiar with. These are just going to sort of be a reference point for us. So moving into part one, what we're going to do is we're going to work on solving equations. And these equations are going to have numbers written in exponential form. The main thing that we're going to focus on when trying to solve these equations is to get the bases to look the same. So the problem starts out as 3 to the x equals 9 to the 4th. What we want to do is we want to look at the bases that are there now and see how we could write them using the same base. We should recognize that 9 can be written as a base of 3. And previously when we had worked with bases, we wouldn't have been given 3 to the x equals 9 to the 4th. We would have just been given 9 to the 4th and been asked to simplify it. So now we're just taking what we know about writing with base numbers and extending it to this. So if we were to rewrite that on the right-hand side, now our equation would be 3 to the x equals the quantity of 3 squared raised to the 4th. Now that we've got that, we use our exponent rule of raising a power to a power, which we know is to keep that base and to multiply the exponents. So now we're going to end up with 3 to the x is equal to 3 to the 8th. Once we get it to that point where we've got the same base numbers, we don't have any other simplifying to do, now we should be able to say that we can set those two exponents equal to each other. And so our final step then is to say that x is equal to 8. So this is one of our more basic problems, but it's really going to be the foundation for all of the others that we do. All right, so let's try example 2. We've got 2 raised to the 5x, and we have 4 raised to the 2x minus 1. We know that we can rewrite 4 using a base of 2. So we'll start by writing 2 to the 5x equals 2 squared. And you want to make sure that you have that in parentheses because that is getting raised to the 2x minus 1. And if it helps you to remember that we have to distribute, you can put parentheses around that as well. So now that we've got a power to a power, we need to multiply those exponents. So we'll end up with 2 to the 5x equals 2, and then we've got to distribute that 2 through. So 2 times 2x gives us 4x, and then 2 times negative 1 will give us negative 2. Now that we have these two written with the same base, we've got all the simplifying with the exponents taken care of. Now we can take those two sets of exponents and set them equal to each other. So I'm going to change colors here, and we'll have 5x equals 4x minus 2. And now this is just a basic algebra 1 problem. We need to collect our x's on one side. Easiest is just to subtract 4x from both sides. So then we end up with x being equal to negative 2. All right, why don't you give example 3 a try? Take a look at those bases and see how you would rewrite them, and then check it against my work. Now when you look at 4 and 64, we should know that they both can be written with a base of 2, but they also can both be written with a base of 4. So if you want to avoid more work than you have to do, we might as well keep what's on the left side with our base of 4. And then we'll rewrite the 64 with a base of 4. So that would be 4 raised to the, oopsies, put that in parentheses, 4 raised to the 3rd power, and then that's being raised to the x minus 3. Now we're going to want to simplify that, so raising a power to a power, we'll make sure we multiply. So 4 raised to the x plus 35 equals 4 raised to the 3x minus 9. And be really careful. Some of the most common mistakes that I've seen people make in the past is really just forgetting to distribute the full way. I see people leaving it as 4 to the 3x minus 3. And then from that point on, everything's sort of shot. All right, so now I'm running out of room, so I'm going to bring this up over here. Now we can take a look. We've got the same bases, so let's set those exponents equal to each other. So we've got x plus 35 equals 3x minus 9. And again, we need to get our x's together and our constants together. And you can do this whatever order you want. Get the x's on the left and the constants on the right, or vice versa. If we do all of our legal algebra steps, we should be good no matter which way we go. I'm just going to subtract 3x from both sides. Negative 2x plus 35 equals negative 9. And then I'm going to subtract 35. Excuse me. And so we'll end up with negative 2x equals negative 44. And we'll divide both sides by negative 2. And so we get x is equal to 22. All right. So far we have worked with bases that are integers. Now we're going to look at bases that are fractions. So if you think about these bases that are fractions, and really I should put parentheses around this. It's 1/4 raised to the x, not 1 over 4 to the x. All right, so we've got 1/4 raised to the x, and we've got 1/8 raised to the x plus 4. And what we really need to think about is the fact that 1/4 means the same thing as 4 to the negative 1. Now, writing that as 4 to the negative 1 and writing 8 to the negative 1 could be a starting point, or we can sort of leap to the fact that both 4 and 8 can be written with the base of 2. And then understand that we can't say that 1/4 is 2 squared, but we can say that it's 2 to the negative 2. So let me write this down and just make sure that you're absorbing what I've just said. Okay, so think about what you know about negative exponents. 2 to the negative second really means 1 over 2 to the second, which is the same thing as 1/4. Be careful. Sometimes people forget the negative exponent. They just write 2 to the second and they'll write 2 to the third. So this has to be 2 to the negative second raised to the x, which means that the 1/8 we can rewrite as 2 to the negative third, and then raised to the x plus 4. So now you can see we've got the same base. We've got bases of 2. Now we've got to do our power to a power. So we'll have 2 to the negative 2x equals 2, and then again, careful with your distributing. That'll be to the negative 3x minus 12. Now we can set our exponents equal. So we'll have our negative 2x equals negative 3x minus 12. Go ahead and combine like terms, get those collected. This will give us x, and that gives us negative 12. All right, moving on. You try example 5. Please try this on your own. Give me a pause and see if you're able to get this to work out. If you can understand this, then you're in good shape for this part of our notes today. All right, so both 2 and 16 can be written with a base of 2. Because this is 1/2, we'll write this as 2 to the negative first, and then raise it to the x minus 3. Now, be careful, the 16 is not 1 over 16. It's just the integer 16. So we get to keep that as 2 to the positive 4th. Don't assume just because one side is going to have a negative exponent that the other side has to have one. Okay? Every case is individual. All right, so now we'll raise our power to a power. So this will give us 2 to the negative x plus 3. And this will give us 2 to the 12x plus 4. And now that we've got that all simplified, we'll set these two equal to each other and go ahead and start solving. This time I'm just going to add x to both sides. And then I'm going to subtract 4. And then I'm going to divide by 13. So there we go. Hopefully if you've got questions, you'll ask me about them. Otherwise, rewatch this part. But I think if you feel comfortable with your bases, that this shouldn't be a big deal. Okay, we're going to move on. Part 2, we're going to write exponential functions. So again, I've got the parent equation here, the y equals ab to the x. This time we're going to look at what each of these pieces really means. Before we graphed them and we talked about what it meant for the asymptote, what it meant for the y-intercept, that sort of thing. But now, what does it really mean when we're talking about a story problem, real life application? You can see that y is our ending value, whereas a is going to be the initial value. So if we're talking about growth or we're talking about decay, maybe we're talking about the number of cells that we started with, and after a period of time, the number of cells that we've ended with. Or maybe we're talking about a population. What was the population in year X and what was the population 20 years from then. Okay, so initial and ending values. B is going to be the rate of decay or growth, and then the exponent x represents time. So we're looking at the number of years that have passed. So in example 1, we are looking at population. We've got the year 2000, and we've got the population of Phoenix as being 1,321,045. By the year 2007, the population was 1,512,986. We could really think about this as ordered pairs. So in part A, we've got an exponential function that can be used to model the population. We're going to write x in terms of the number of years since 2000. So if we wanted to, we could write this as the ordered pair 2000 with that population, and then 2007 with population, or we could think of it as 0, because the year 2000 is our starting point, and then this would be our y-coordinate, and then this one would be 7, and then that would be our y-coordinate. So if we're going to write a function that would be used to model the population, we're not going to expect to be able to fill everything in. But what should we be able to fill in? Well, our initial value would be that initial population. So the initial value would be this. That would be our A. Then our ending value would be that population in 2007, because it's after that period of 7 years. So ending value would be our Y. 7 is the number of years that have passed, so that's going to be our time. And so our unknown is going to be B. That's what we're going to be figuring out. What is that going to be, so then we could come up with an equation that would work for us to predict their population after any number of years. Okay, so here we go. So we'll write down y equals AB to the x. And we'll start subbing these things in. I'm going to move this down a little bit. There we go. So we'll have 1,512,986 equals the initial population. And then we're going to have b raised to the 7th. So we're in good shape when we just have one variable. Now, what are we going to do to get b by itself? The first thing we're going to do is we're going to have to divide. So we fall back on our normal algebra skills here. Divide both sides. And so then we're going to end up with b to the 7th. And let me do the math here, my handy dandy calculator. And we get this really long decimal. We get 1.145294823, blah, blah, blah. I am good if you write it out to a few places, maybe 1.145, and just put some dots. That way at least I know that you've done the first step correctly and that you're in the right ballpark. Now the big question is, how do we get from a b to the 7th to just a b? We're used to taking square roots of things, but in this case what we're going to have to do is we're going to have to take the 7th root of both sides. Now how do you do that? Well, if everybody's got this TI-30X2S calculator or something similar to it, you'll see that there is a second function. It's under the little kind of caret top key. So if you look above the x squared button, there's a key there that's got this thing. And as a second function, it has an x within the root. So what that allows us to do is it allows us to take different roots. So 7th roots, 8th roots, 5th roots, anything that's not, going to be hit by that square root key. So if you leave this decimal, the whole shebang, on your calculator, and then if you just type in the 7, because we're hitting the 7th root, hit your second button, and then hit that caret top key, you'll see it'll say 7, and then it'll have a little exponent of x with the root symbol. And then if we want to just grab our old answer, instead of trying to type in that whole big long number, we'll just hit the second button again, and then hit the little minus sign down the right bottom. Because you can see as a second function, it grabs your last answer. And so what you'll see on your calculator, it'll look like this if you've done it right. It'll be 7, little exponent, and then this, and then A and S, and then you'll have this flashing cursor. So give it a try, and then hit enter. And again, you're going to get this decimal. It's going to be 1.019569316. I'm just going to have you round out to the nearest hundredths. So instead of putting an equal sign, I'm going to put an approximate symbol. That would be approximately 1.02. Okay, so now we're not done. Okay, we've gone through all this work and we found B. What we need to do now is we need to sub that back into this. So what we're going to do is we're going to say y is going to be equal to, and then we're going to have our b, and we're going to have our initial value, so 1,321,045, 1.02, and then our x. So the x and the y are going to stay x and y. What that allows us to do then is to say, well, why don't we estimate the population of Phoenix in 2017? I mean, that's where we are now, right? We're 10 years later than this data. And so if we use x as 17, we'd be able to sub that in, and we'd be able to estimate the population of the city. It'd be interesting to see if it's even close to what they have now. You know, this is assuming that their growth stayed on pace for what it had been doing from 2000 to 2007. Okay, so this is all modeling, this is all predicting. And that's really what math and statistics and probability and stuff are about. Okay, let's look at example 2. Let's see if we can apply it to something different. So y equals ab to the x. Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. And we're going to write an exponential function that could be used to model the number of bacteria after x hours if the number of bacteria changes at the same rate. So looking at what we've got here, here is our initial value, which is going to be our a. 4 hours is going to be our time, so that's going to be, actually I shouldn't put t, I should say x. And then 23,000 was our n value. That was after 4 hours, this is how many cells we had. And so again, you can see that it's the b that we don't know, but we'll be able to figure that out. So we'll sub in our numbers, 23,000, initial 7,500. We don't know the growth or the decay, although you can tell it's growing, right? And then x is 4. So now in this case again, we're going to do the math and divide. So now we'll have b to the 4th. Let me do the math here quick. 23,000 divided by 7,500. Again, this time we get 3.06, and that's repeating, so I'm just going to put that down. And rather than taking the 7th root, now in this problem we're going to have to take the 4th root. Be sure you put the little index number, otherwise it looks like you're taking the square root. So now b is going to be approximately, now again, you've got this number on your calculator, just go ahead and type in the 4, hit your second key, and hit that caret key, so you're taking the 4th root, and then grab your old answer. And you can see that it's approximately 1.32 if we round it out to the hundredths place. So again, what's the equation that's going to model this change? Y stays the y, grab your initial value, which is 7,500, use your 1.32 that we just found, and then raise it to the x. Uh-oh, all of a sudden my smartboard doesn't want to work. There we go. It's not let me do that now. There. So let's raise to x. Now, example 3. Example 3, instead of being put into a story problem, you're just given 2 ordered pairs. So who knows? This could be population, this could be employees, this could be cells dividing in a petri dish. This could be a strep test. We have no idea. But again, if you know all the pieces and parts, because this is 0, this has to be our initial value right there. So there's our A. And then this is going to be our X, because that will be how much time has passed. And then this will be our Y. That will be our end value. So 3,125 equals 5b to the 4th. You can tell this one's going to work out nicely. Divide by 5. And when we do that, we get 625. Now we're going to take our 4th root. And b is going to give us 5. Because 5 to the 4th is 625. So now our equation, y equals initial value times our b raised to the x. There we go. Once you get the hang of it, once you figure out identifying that initial, value, the end value, it's not bad. Okay, moving on. Part 3, compound interest. Now, I'm doing this on the same day as the other notes, but it's possible that we're doing this on a second day. Depends on if my schedule works out as planned and, all that jazz with any weather-related things and stuff like that. So I'm just going to keep going, and I really only have one example for this. Compound interest is the way the banks really figure interest for your accounts. When you are in 7th grade, you learn how to do simple interest, I equals PRT, but it doesn't take into account that you're earning interest along the way, and that amount goes into your account, and then you start earning interest on the interest. It also goes in the other direction too, if you're borrowing money. Okay, you're paying principal off, but you're also paying off interest. And so the amount of interest is going to get less and less as the amount that you owe decreases. So compound interest is the real deal. I would call simple interest more of an estimate, kind of just to give you an idea of how it all works. This formula is a little more complicated looking than our simple interest formula. Now A is going to stand for the amount in the account after T years. If you remember with I equals PRT, I stood for just the interest earned or the interest paid. And then if you wanted to know how much was in an account or whatever, you had to take that and add it on. This just, boom, tells you the amount. Squares right there. Now T has to be years. And so keep that in mind. If you're given 6 months, then you're going to have to use 0.5 because it's related to years. P is the principal amount invested, or on the flip side, borrowed. R is the annual interest rate. And the thing that people often miss is making sure that that's written in decimal form. So remember, if it's 7%, you move the decimal 2 to the left, it would be 0.07. If it were 2%, you move the decimal 2 to the left, it's 0.02. If it were 1.5%, move the decimal 2 to the left, it'd be 0.00, 0.015. There we go. So make sure you're moving that decimal. N is the number of compounding periods in a year. So for instance, if I said it's compounded quarterly, how many quarters are in a year? Well, there are 4. If I said monthly, how many months are in a year? There are 12. If I said semi-annually, well, semi means 2, so there would be 2 in a year. So you're going to have to look carefully at what those words mean. And if you're not sure, ask. So here's our one and only example. And again, it's really important for you to write down all the numbers, put it into that equation, because then I can give you some partial credit if for some reason your calculating goes haywire, which happens. So an investment account pays 5.4% annual interest compounded quarterly. So here's our signal for our N. $4,000 is placed in this account. We want to find the balance after 8 years. Some of you who really like to organize things might want to just sort of a list of all these letters and what they're going to be. So if it pays 5.4%, that would be our rate. And 5.4%, if you move that decimal to the left, bloop bloop, would be 0.054. A is what we're trying to find. so we aren't going to know that. P is the amount invested, and we're told that that's $4,000. Then we're looking for N, and N is the number of compounding periods. They told us quarterly, so N is going to be 4 times a year. And then T, the number of years, we're looking at a balance of after 8 years. So there we go. So A equals P, taking 1 plus R divided by N, raised to the N times T. Okay, so let me extend this here. There we go. So A is going to equal 4,000. 1 plus 0.054 divided by 4, raised to the 4 times 8. So this will be something that I'm looking for. Did you sub in all the right numbers? Then we'll do the math. So let me change colors here. So A is going to be equal to, and order of operations, well, we can take care of that exponent. Let's do 4,000. And in here, if we do the 0.054 divided by 4 and add it to 1, it's going to give us this, raised to the 32nd. Okay, so that would be the minimum I would expect to see. Now, if you want to show me what you got when you raise that number, let me do this here quick. If we want to raise it to the 32nd power, it's going to give you a nice full calculator. Now this step is optional, but then I would at least be able to see if you're on the right track. And again, I would just want you to round it. So it's about 1.54, let's say. Maybe put some dots so you know that I know, or I know that you know that there's more to it. Keep that number on your calculator, and then multiply it by the 4,000. Don't use the number that you rounded it off to, or else your dollars and cents are going to be off. And then what I want you to do is I want you to round it to the nearest cent. Don't write out this long number because you would never be paid something that looks like that. And remember, when we're rounding, we're not just chopping the number off. This gives us 6,143.559, blah, blah, blah. So that tells us we're going to have $6,143, and the 0.559 would tell us that we were going to round it up to 56 cents. So just be careful with your calculating. I know sometimes people just try to type the whole shebang in using their parentheses and all that stuff. And more times than not, people forget something. They put the parentheses in wrong or whatever, and it just ends up being goofy. You know, make sure that your answer makes some sense. You know, I mean, if you get something like $6 million and you've had, you know, your money in for 8 years at 5%, I mean, would that really make a lot of sense? I don't think it would make sense even to you. I mean, I know you guys haven't had a lot of experience with money, but if it seems like it's really off, that's the signal to you that maybe I should try it again. Or maybe instead of using 0.054, you use 5.4, which would be like 540%. And that's going to give you a wacky answer. So really just, you know, think about it a little bit. Look for numbers that just seem really out of whack, and double check. Kind of like measuring twice and cutting once. You know, calculate twice. All right, that's it. It's a lot of information today. So let me know if you have any questions, and good luck.